Okay, so the title of my talk is Optical Feedback Interferometry for Raster scan Profilometry. And it's a work that has been done at the LAAS-CNRS of the University of Toulouse by some of my colleagues that are listed here. Sorry, not working very nicely. How can I do that? No. No. Sorry, I don't know how to do it better. So let me say a little words about the optical feedback interferometry first. Well, pretty much everybody knows what is standard interferometry, and if you have been working with, you know that usually there's a lot of optical elements like beam separators, quarter wave, and everybody knows that the alignment is something that is very tricky. So optical feedback interferometry is exactly the contrary of that. The idea is that the laser diode, the laser in general, is the light source, but also the interferometer and the sensor. How does it work? Basically, a laser is beaming onto a target, and some light is captured back inside the laser. This light will interfere with the inner wave inside the laser cavity, and will produce variation of the optical power of the laser. So the advantages, of course, is that this system is self-aligned, and it eliminates pretty much all optical devices, apart for the lens. But sometimes we have been proven that it can work even without lens, considering that the distance of operation is short. So again, okay. Well, the counterpart of this is that the simplicity of the setup comes with a complexity in the modeling. So I wrote here to show you that there is a lot of physical background behind what I'm saying. But basically, rate equation of a laser have been extended to take into account the optical feedback. And Lang and Kobayashi in the early 80s have done that very well. So you see the two blue terms are representing the feedback in the rate equations. I'm really sorry that it does not present everything. Okay. Well, what you need to remember is that the optical feedback impacts the amplitude of the field, so it impacts the laser power that is emitted, the phase also of the light that is emitted by the laser, but eventually it affects also the carrier density. So there is ways to get the information directly on the junction voltage of the laser when it's a laser diode. These are the three usual sensing schemes that you can use with the optical feedback interferometry. So the first one is the displacement measurement. In this case, there is a change in the external cavity, which is the distance between the laser and the target. And this is monitored by the time of flight. Also, you can have velocity measurement based on the Doppler effect. So the beating will be with the backscatter wave that is Doppler shifted. And you can also have absolute distance measurements. In this case, you need to modulate the laser diode by modulating the current in the laser. Then it will change the wavelength, and the light that will come back will be in frequency shifted as compared to the one inside the laser itself. So now let's go to profilometry. So it's not the first time that profilometry has been tried with the optical feedback interferometry. The first work was done by Özdemir in 2000, and it was using mostly statistical analysis of the speckle effects, and it uses very important neural network and deep learning methods to work on these speckle signals. The second one is work with with a laser that emits two different wavelengths. And in this case, well, you need to have a mathematical expression with the two signals that you get from the two different wavelengths. And this has been published recently in 2016. But it works only with a very specific type of laser that has these two wavelengths. The third work has been done by Herbert and by Bertling. And basically, the idea is that if you do modulate the laser signal, mostly with an optical chopper or by modulating the injection current, Well, you can get information based on the phase of the signal. You can get information on the actual distance between the laser and the target. So now, the idea that we had is that raster scan is pretty much, why are we not using something that is as easy as the conventional optical feedback interferometry sensor, which means just the laser shooting on a target. And the idea that we have is that if you consider a laser that is scanning a target with a structured surface, like on the left side of this figure, well, this could be equivalent to, what you will observe with vibrations. So on the right side of the figure, you see what you get when you have vibration. And in both cases, you can consider that the distance between the laser and the target are just a constant term L0 and a variating term LT. Getting worse and worse. Okay, so what we have done to test that is that we have built a target that is it has a sinus shape. We did that with a 3D printed system, and we did a sinusoidal shaped surface with a 5mm height. Okay, the result that it was completely impossible to obtain any interferometric signal. So that means no periodic fringes using this target. So we tried to figure out what would be the reason. So we first found to the disk Wobble. Okay, yeah, the target is mounted on a disk that is rotating through a motor, and any misalignment of the disk, the central axis of the motor, will induce unprecedented wobble on the target. The second thing that we thought is that since we were using a 3D printer, we know that these devices will give the surfaces that are not very clean. And we think, okay, what if the structure is very rough and the roughness is superior to half the wavelength? Then in that case, there will be extra fringes that are not due to the sinus shape. And we believe that it will induce extra fringes that will destroy the system. The second thing that we thought is that also due to the granularity of the surface, there could be too much speckle, so too much noise. And the last idea that came is that maybe just the fact that the laser beam has a dimension, and this dimension is not neglectable, will affect our signal. So if you see on the figure on the bottom, so from one point of the laser beam to the other, there will be a shift in the distance, delta L, that could be of importance if we take that into account. So we first thought how to represent that in the mathematical model. So the hypothesis is that we will reduce our spot size to n scattering elementary surfaces, and we will add each contribution of each surface to the back scattered power. This model actually was already used in the case of multiple scatterers, in the case of flowmetry, for example, where you have scatterers in the flow and you can consider several particles. So the resulting expression, I passed to you the solving of all the equations I've shown before, is that the output power will be a sum of contribution of cosine function, depending on the distance of each elementary surface on the disk to the feedback power. So that was for the modeling, but then comes the valid experiment that we wanted to build. The idea was that we wanted a pure change in the external cavity length, okay, that will not be vibration. We've seen that with scanning a rough surface, we will have a lot of issues, as I already mentioned, the speckle, the wobble, etc., etc. So we decided to go from scanning to tilting the laser onto a very flat surface that is free of speckle. That means a mirror. So the advantages, of course, is that in this case there will be no speckle, no wobble, and we will know very precisely the variation of the distance. The drawbacks is that when you go tilted on a mirror, then the light does not come back toward the laser, and it is tilted, it is reflected elsewhere. So the power that is fed back will vanish, and the signal, of course, will vanish too. Okay, so we built this setup to solve this issue with laser diode on the right side, then focusing lens, and we added a tunable optical density so that we can be able to detect the signal even when we are in front of the mirror and when we are slightly tilted. To do the tilt, we use galvanometer okay, well, you see the details of the laser, etc. And so that using the tunable optical density, we always have the signal visible. So what is the model saying? The simulation is saying that with the conventional model, we should have 13 fringes. But with by taking into account the beam size on the target, then we get up to 18 fringes. And as you can see, because here we do not take into account the fading in power that is fed back, but you see that the signal is drastically fading because of loss of coherence in the light that is coming back. So here are the experimental results that we observe. Okay, so we cut the variation in angle in 4 parts. So I will only present the A and the C. So the A is from 0 to 0.5 degree, which represents 2 micrometer of changes in the external length. So the model predicts that there will be 3 fringes, and we see that there are 3 fringes, 3 very visible fringes. And then on the other end of the 1 degree tilt of the mirror, then we have 5 micrometer difference of change. And what we can see is that the fringes are not more visible, even though that we remove the optical density. And more important is that they are not coherent at all. That is not absolutely periodic like we should have obtained. So we see here that we do have this loss of coherence. So as a conclusion, what we demonstrate is that we have an efficient model that was previously used for flowmetry with optical feedback, and it is working well when you want to take into account the size of the laser on a target. And that is some important tool. The second thing is that raster scan profilometry can work as long as the roughness over the airy disk of the laser spot on the target is less than λ/2, and that is very drastic. So it means that in most of the cases, it will not work. It cannot work with the actual laser and the actual optics. So what are the perspectives with this method? Well, what you can do is to increase a lot the laser wavelength by using intraband cascade laser or quantum cascade laser. And then you can, by increasing this wavelength and reducing the spot size, maybe on certain targets, then you can do a very fast and very efficient raster scan. So this is the end of my talk. Thank you very much for your attention.